We as humans have this weird fascination with time travel, all the way from the early sci-fi TV shows such as Doctor Who, all the way back in the 60s to even modern releases, for example Avengers Endgame. What is it about the human mind that is so enthralled by time travel? Is it perhaps in human nature to make mistakes and constantly want to go back and change the past? Oh, sorry. Where was I? Well, from a physics point of view, time travel is one of the most difficult problems to solve. But we can start from basics. One of the first, most influential theories that talks about how time can be manipulated was Einstein's theory of special relativity, and more specifically, time dilation.
Let me get to spitting, cause I'll hit you with physics. Cause these equations are amazing, stay alert and look busy. You better sharpen up your shape and get ready to learn, so we can teach you all the physics from your classroom to CERN. Alright, stop.
Today, time dilation. Before we get going, we ought to define a few terms that I'm going to be using throughout the video. The speed of light. The speed of light is like a universal speed limit. Nothing with mass can travel faster than it, as to do so would require an infinite amount of energy. And to put a number to that, the speed of light is 300,000 kilometers per second. A reference frame. For the sake of this general overview, we can probably use it interchangeably with point of view. When an object is moving, we describe how fast it's moving with a velocity. And depending on your reference frame, depending on your point of view, the velocity of an object might be different. The best way to understand this is by looking at some examples. Let's say I threw a tennis ball in the air at 10 meters a second. Now, from the point of view of me standing on the earth, or from my reference frame, I see the tennis ball moving upwards at 10 meters per second. However, an ant sat on the tennis ball wouldn't see the tennis ball as moving, as they're moving together. So from the ant's point of view, the tennis ball is stationary. It's the earth that's moving away at 10 meters per second. So, in the reference frame of the ant, the ball is stationary. So now you can see how velocities of objects are different dependent on whose point of view you're watching from. Another example is if you and your friend are going on a run. From the point of view of an observer standing 10 meters to your left hand side, they see you and your friend running at, say, 3 meters per second because I'm absolutely rapid. However, now you look across at your friend and from your point of view, they're stationary. From your point of view, in your reference frame, your friend isn't moving, the rest of the world is. Do you see what I mean? Space-time. I'm not going to talk about space-time too much here because we don't have the time for that. However, we do have another really good introductory video about space-time on our YouTube channel or on the website. Special relativity is a theory formulated by Einstein which talks about what happens to objects when they start moving very close to the speed of light. General Relativity, another theory from Einstein. What a show-off. This considers the effects of acceleration and gravity on the curvature of space-time. Okay, definitions out the way. Now let's talk about how we can make time do funny things. Enter time dilation. There's a saying that you hear a lot in physics which is, fast clocks run slow. But what does that actually mean? It means that from the point of view of someone who's moving very, very fast, to them, time will run slower than someone who isn't moving as fast. And this is a complication derived from Einstein's theory of special relativity. Special relativistic time dilation states that the closer you move to the speed of light, the slower you experience time. Let's use the example of a spaceship setting off from Earth, heading to another planet that's 10 light years away. The spaceship is travelling at 90% of the speed of light. Now, from the point of view of someone on Earth watching the spaceship fly away, they can do a rudimentary calculation using time equals distance over speed. They find that the time it should take the spaceship to get to that planet 10 light years away is about 11 years. However, from the point of view of the crew on the spaceship, in the reference frame of the spaceship, they experience time slower as they're moving close to the speed of light. So from their point of view, the journey only takes about 5 years. If you want a more in-depth, more mathematically rigorous treatment of this situation, you can check out the advanced explanation section on the PIMDB website. So sure, time dilation isn't time travel in the sense that you can go back and change the past. It more talks about how time can be experienced differently dependent on what situation you're in. General relativistic time dilation states that the closer you are to a massive object, the slower you experience time. If I was a spaceman sat at the event horizon of a black hole, because I'm closer to a massive object, I will experience time slower than anyone who isn't. I probably also wouldn't be here right now, because I definitely would die. It's hypothetical, I guess? Now you may be thinking, Johnny, when am I ever going to be stood on the event horizon of a black hole? Who cares about general relativistic time dilation, because we're never going to experience it? But that's where you're wrong. Black holes are an extreme example because they are incredibly massive, but this effect even happens on Earth. GPS satellites orbiting closer to Earth will experience time slower than other satellites who are orbiting further out. And because GPS satellites need to make such precise measurements, that very small difference in how they experience time can actually have large snowballing effects. Now this general relativistic time dilation isn't seen as much in movies and sci-fi, but it is mentioned in Interstellar. If you'd like to see a breakdown of how Interstellar treats physics, then by all means head to our review page of Interstellar on the PIMDB website. I hope this video has been helpful and I hope you enjoyed it. If you've got a question or you'd just like to start a discussion, the comments section is always open. If you're interested in space-time, superconductors and quantum entanglement, by all means check out our other introductory videos on our channel in this playlist here. Thank you guys for watching and I'll see you in the next video. See ya!